So we shall start the function then. Yeah. So good afternoon, everybody. So today is the celebration of National Mathematics Day. Usually, National Mathematics Day is celebrated on December 22nd. Since that is going to be a holiday, so we're preponing the celebration and celebrating. So to start with this function, I request Dr. Manjunath Prasad to give the overview of this function as well as to introduce the program. Sorry.
Overview, nothing. Just Good afternoon, everybody.
Good afternoon, sir.
So I welcome everyone, my colleagues, Professor Harikrishnan and Professor Chakravarti, and other friends and participants of a national workshop. Of course, I welcome online participants also. So this afternoon, we decided to have this National Mathematics Day program. Usually, we used to conduct it on 22nd of December for many years, probably since 2016 at least. We were organizing this National Mathematics Day, particularly theorems with the mathematics department and other statistics. At that time, it was statistics department organized this particular National Mathematics Day combined, and used to enjoy a day remembering Ramanujan. It is very much required for we are very much proud of Ramanujan because he is the greatest mathematician ever we saw in India. And at this very early stage, he had gone to England and worked with whatever. I just missed this thing with the professor over there and did lots of research. In fact, many of his work were written very shortly, and people are still struggling to understand it now. Around at the age of 32, he expired, and before that, he did lots of work. We are all proud of him, and remember him may inspire many young people like you to work in his line and contribute more. It may not be exactly in the area of number theory, could be in any area. If you people can try to reach this level, make an attempt, then it would be a great. So we will have many more Ramanujans in India. So because of a holiday, we will be organizing this particular program in this afternoon with a limited number of faculty who is available and research scholars and other participants of this national workshop. I welcome you all, and to tell about overview. I don't think there is much. Professor Chakravarti will be delivering a technical talk. He will also talk to you a little more about him. And after this, probably Suvendu will.
Sandeep.
Sandeep.
I will just give an
Okay.
overview of Ramanujan.
He will give an overview of
Ramanujan.
not overview about his life. Okay. I welcome you.
Thank you, Manjunath sir. So as he has already explained, Ramanujan was one of the all-time greats of India, especially, and Hardy and Littlewood consider him.
Hardy, I missed his name. Sorry.
Hardy and Littlewood even compare him to Euler and Jacobi. So this year, every National Mathematics Day is celebrated to honor his birthday. So this is the 137th birth anniversary of Ramanujan. So on this National Mathematics Day, so
I'll just talk something about Ramanujan and I'll quickly hand it over to Harikrishnan sir. So Ramanujan spent 5 years in Cambridge collaborating with Hardy and Littlewood, during which he had produced many pioneering works. One was in providing a rapidly converging series for pi, which has many computing applications. Many algorithms, data structures, all these are based on his functions, based on his study in special functions. More than that, one of his pioneer work was in the theory of partition functions, about which Professor and about other Ramanujan tau function, all these things. I hope Professor Kalyan sir will speak more about those. So, I would like to stop with this final remark. The theme of this year's mathematics day is the bridge to innovation and progress. So this is to emphasize how mathematical principles underpin advancements in science, technology, and innovation. So in this context, what I would like to add is Ramanujan's study have influenced not only mathematics, but also in the development of several algorithms, data structures, and mathematical tools in the field of computing. His special function theory, as I was telling, is applied in the calculations pertaining to filtering out background noise in your phones and for obtaining lifelike video game graphics. So in optimizing certain calculations, Ramanujan's algorithms have been used. And finally, his work on mock theta functions was also crucial in the study of mathematical physics, in particular in the black hole theory. So with this brief account of his work, I hand it over to Professor. I would like to hand over to David, who will take it up. Yes.
Thank you, Dr. Sandeep, for a good overview of actually his life of Ramanujan and giving us some good memories of it. So now I'd like to actually call all the people in the dais to have a honor for Srinivasa Ramanujan with a floral debate. So I invite everyone to join the gesture of respect and remembrance.
Others also quickly come in. Yeah. First. Yeah, don't wait for invitation. Quickly finish.
Lavanya, I don't know all names, that's why I'm calling round names.
Thank you, everyone. Now I'd like to call upon Dr. Kunjan Sankar sir. He's a head of the Department of Mathematics, MIT, to share a few words with us.
Thank you, Dr. David. Respected Kalyan Chakrabarti sir, Dr. Manjana Prasad sir, my colleague Hari Krishnan and Sandeep Srinivas, and my dear students, research scholars, and online and offline participants. It's a great privilege here. And even though this is the vacation, very few of them are joining, but the program is well conducted last 2 days, and today's program, National Mathematics Day preponed. And it's a good that we are remembering all the contributions of Srinivas Ramanujan. And in 2012, I remember that the government has initiated this National Mathematics Day, and the government has recognized the contributions of Srinivas Ramanujan. And before that, also everyone aware of that. But later, because of this National Day, everyone is celebrating, almost all the institutions, reputed institutions in India, celebrating this event. And only one thing is that this is fall under vacation, even semester, odd semester vacation. So sometimes very difficult to get the research scholars or faculty or something. But still, this time we are able to convey the information, and most of the faculty and students joining online, apart from the offline participants. So I wish you all the best and keep doing the good things, and even we hope that we will be able to conduct in the future this particular day every calendar year. So I wish you all the best and very good and advanced new year. Thank you.
Thank you, sir. Thank you for your words. Now I'd like to actually call Dr. Hari Krishnan, faculty of Department of Mathematics, MIT, to introduce our esteemed guest speaker for today.
Good afternoon, everyone. I would like to introduce our today's speaker, Professor Kalyan Chakrabarti sir. We are glad to have Professor Kalyan Chakrabarti sir as the speaker of the Ramanujan Lecture Series to celebrate the occasion of National Mathematics Day 2024. Professor Kalyan is currently the head of the Department of Mathematics at SRM University, Amravati, and formerly held positions as the Director of Kerala School of Mathematics and Professor at Harishchandra Research Institute, Prayagraj. He works in the area of number theory, more specifically in the areas of algebraic number theory, automorphic forms, special functions, and elliptic cryptography. He completed his PhD at HRA Prayagraj in 1997 and went on to do postdoctoral fellowships at IMSC Chennai and Queen's University, Canada. He has visited many esteemed universities around the world and has established wide professional collaborations. He is the Vice President of the Society of Special Functions and Applications and the organizer of the annual International Conference on Class Groups. A prolific researcher, Professor Kalyan has to his credit more than 60 journal publications and has various books as well. In 2024, he was awarded the Ganesh Prasad Memorial Award by Indian Mathematical Society, and in 2021, he was elected as a fellow of the West Bengal Academy of Science and Technology. He has guided and mentored many PhD and postdoc students during his career. And those who have met him, you can see that he is a very good physics person. So that is also that he is keen on his fitness too. And with great pleasure, I invite him for the program and hand over the session to Professor Kalyan sir. And he will be delivering a talk on titled Ramanujan, a brief journey to his life and work. And one more thing I want to brief. This year, sir is completing his 60 years, and here, so that it already completed in May. 2024. That's why he moved from HRI to SRM University. So I wish you happy birthday also, sir. It's a belated one. Still, I am wishing you. So handovering to you, sir.
Thank you so much. And, it's real pleasure. So let me try to share my slides, then I will talk about. So is my slide visible?
Yes, sir. Yes, sir.
Let me see, it moves. Yeah, it moves. Yeah, so let me begin, and let me first be really grateful to all of you to give me this opportunity and such good wishes, good words. Good wishes and good words always help help always in every phase of our life. And it's really pleasure to be, even though online, to be present amongst you today on this day of your celebration for National Mathematics Day, to celebrating Ramanujan. And already you have heard some few things about Ramanujan, and then here in my talk, I will try to kind of tell you that the kind of life that he had, along side by side, other informations, plus some of the works. I'm not going to. The talk will not be technical at all. It's just to try to tell you the beauty of some of his works in words, maybe not into any technical things, and we'll try to emphasize on you that there is a lot of things still we can follow from Ramanujan's life itself. And mathematics is the other side, but life also, that once you have some aim and vision, then no matter what the situation is, if you try your best, you are mostly going to avail that, going to achieve that. So that at the end, but let's move forward and try to see. I mean, all of you know, all these facts are very, very well known, been talked all over the world. But to this particular day, when you are celebrating his birthday, preponed, but this whole month is being celebrated as his birthday. So to really again go back to the things that had affected him, that has affected his mathematics, and try to go back to that era and try to see that what kind of work that he has done. And given the life that he had and the work that he has done, you will realize at the end of my talk that a real gem, a real genius. And let's see, I mean, if I can convince you people, all of you know, but here is a brief account of his life and some of his works, very few. Okay, so let me move. So this is the picture that you find most of the places, Ramanujan's picture. And this is the picture which was in his passport when he went to England. And this picture was not available. In fact, if you remember another Nobel laureate in physics, S. Chandrasekhar, so he was also from Chennai, in fact, Tamil Nadu. And he was great fan of Ramanujan because he was also there. And then Hardy requested Chandrasekhar to really look for this, his passport, this particular photo. And actually it was he, S. Chandrasekhar, who really found this photograph and handed over to Hardy. And then it becomes so famous, this particular photograph, which was in his passport, in fact. So as I told you that I'll be like a storytelling, and I'll try to relate the stories, not just, it's a long story if one has to tell, but I've just picked few things from few places and tried to amalgam them into a talk, and I hope that you'll be able to get a feeling of that. So he was born, as was told, December 22nd, 1887. It was British era at that time, and the place was Erode, where he was born, and it was under Madras presidency. And his father was K. Srinivasa Iyengar, and mother Komalatmal. They were living in Kumbakonam, in that area. And Srinivasa Iyengar was working was a clerk with meager salary. He was a clerk in one of these, some sari shops, as far as I get. And he used to take, keep accounts, etc. And Komal Atmal mostly was a housewife, but then the situation sometimes used to be bad. So she used to sing in the nearby temple. I'll come to that temple. That also has played a very important role in Ramanujan's life. So she used to get, not only singing, used to get prasad in the temple. So sometimes the dinner used to be that prasadam from that particular temple. And another fact which many of you may not know, that Ramanujan had two brothers. And there was, at that time, there was that, this smallpox was that was kind of infested at that time, that area. So two of his brothers, in fact, died because of that. And somehow he survived that. And before I go, I don't know, I'm sure all of you have visited Kumbakonam. And if you are not only just in mathematics, but in science, I would tell you that if you have not been yet there, go and visit. It's in Kumbakonam. It is being restored and taken care of by Sastra University. And you will not only just motivation, you will get a first-hand kind of feeling that, this genius used to stay here. And really, truly speaking, if you go there inside, you'll get a feeling as if, he used to work. And this is the place which is renovated a little bit. All these pillars and also is renovated just to keep the house. And you can see that little area there, that used to be the kitchen there. Here you can see, go inside, there will be kitchen. So now there's a bust of Ramanujan here. And some of these journals and other things are kept there. She was not there. I'll come into his house a little bit more. So about his house. So his initial study was at town school. This is a picture of the town school. And this is another place that if you go to Kumbakonam, you have to visit, because he studied here. And, if you go to these classrooms, you'll find as if it's like a museum. Because all these places, there are memories of Ramanujan that has been kept. And so this is another place that you have to visit when you go to Kumbakonam. He was an outstanding student, as we know, and won many academic laurels, mostly for mathematics. He was awarded a scholarship for showing excellence in mathematics to go to college. From 10th to the college, those days it was there. So he got a scholarship because of his brilliance in mathematics. And he went to take an admission to college by that year thing. But before that, he was already doing research in his school days itself. He was at the age of 13, and he was exploring various things on his own. Like, for example, at the age of 13, he discovered most of the trigonometric identities. Discovered what I'm saying, that he was not aware that, these things are already there. So basically, when he found that S.L. Loney's book, he found that all the things that he discovered, he thought he discovered, was already there. But that itself shows the brilliance of this person, that at the age of 13, he could derive all those identities, trigonometric identities, without help of anything. But, as it happens to many of us who are into research, that many a times you do some research and without knowing, that, somebody must have done it earlier. And it had happened to me also, that I did something and then I found that it has already been done. So all of you go through that thing, that, you feel sadness about it. And Ramanujan was also sad knowing that, that already those things are there in the literature. So before I go to the college, this is one book that at the age of 15, in 1903, he received a copy. This is a library loan copy of a book. The name of the book is A Synopsis of Elementary Results in Pure Mathematics by Kerr. And what is the specialty of this book? You can see the stamp of the university here. And the specialty of the book is that it contains about 6,165 theorems. And it's very systematically written. Systematically in the sense that one by one, with whatever is needed in the next theorem, the results, the notations and all are already there in the first one. very systematically it was reasoned and quite scientifically arranged, as I'm saying, with proofs. And this book played immense effect on Ramanujan's way of writing. And this book also ignited Ramanujan's passion for mathematics. And this was also a major source of reference for him, because he was kind of taking that these are the things that is known, and he was trying to derive similar identities, or trying to give different proofs of those things. So this book really ignited Ramanujan's passion for mathematics, which was already there. And he started writing all his notebooks in the later part was written in this fashion only. For example, you can see, so following this style, he recorded his findings in his notebooks. I mean, you will see, if you see his notebook, it will be something this fashion. Just try to bring people who haven't seen his notebooks, and so you'll be writing like this, one by one. So this is a method that he followed from that book of Kerr, that had a tremendous effect on him during that time of his life. So he got the scholarship, as I told, and he took admission to Government Arts College, that's in Kumbakonam. But by then, as I told you, that he was already exploring various problems in mathematics, various identities, and that book also ignited his passion for mathematics. And he kind of, you can tell that he got addicted to mathematics at that stage when he took admission to college. And all the time he used to be engrossed in mathematics. And because of that, he was unable to give time to the other subjects. And as it had to happen, he failed in most of the subjects. And in the process, lost the scholarship that he got before. And that scholarship was not just for him, it was really helping the family also to some extent. So again, I mean, the poverty loomed large on their family. And basically, literally, he ran away from there. And he came towards Chennai. And then he was in the station, languishing there. Then he met some good people. And he was always carrying his books of his, I mean, the notebooks of his findings. And some people were, very impressed by that one. And they helped him to get an admission to Pachiyappa's College in Madras. At that time, it was Madras. Again, he took admission there. He was trying to clear the FA exam. And he passed in mathematics. And in mathematics also, he tried only the problems that was interesting to him. Not that all the problems he will not try even the other problems. So he passed in mathematics, certainly, and by attempting only those questions, but failed in other subjects. And then he again gave at 1906, once more time Fellow of Arts, that FA exam, but failed. Then he gave up, actually, of getting into this traditional way of learning, getting degrees. And he was no more interested in basically to get a college degree. He left that idea and immersed himself into inventing new mathematics. He used to be sitting somewhere in Chennai, Madras, in a very, very acute small room with acute poverty. And even for food, he had to struggle. And there is a very good account of these things. When his friends used to come to visit him, they would find him sitting on the floor with a slate and a pencil. And he did not have money at that time to buy papers. So he will do everything on the slate. And then whatever the final result, he will write only in the paper to save papers. So many a times you would have just the formulas or the identities, and the proofs won't be there. And so he was living in extreme poverty. And at that time, he had a medical urgency also, needed a surgery. But he did not have money. But again, somewhere or other, he found people to help him out. He got a doctor who did the surgery free of cost. And he was released from that particular pain that he had at that time. So he continued researching on numbers, sitting there and looking for identities, formulas, and kept them jotting onto his notebooks, which is now known for his notebooks, famously known Ramanujan's notebooks. and without any proof. So here is a page of notebook. As you can see, it's very well protected now in Madras University. If you go in the library, you will find that very well protected and saved there. Whichever was found, lost notebooks are also there, which was found later somewhere in England there, which was again by Hardy and Littlewood, all these people, Bushbant and all, they saved those things, and they are in good hands now. So at that time he was going on doing, but he was really leaving into a kind of academic desert. Academic desert in the sense that nobody was able to tell him the kind of mathematics that he was doing, whether it is already been done or not, or where to go from there, how to even get them published and other things, how to tell the world that the kind of mathematics that he was doing. So he was really could not comprehend. People were not understanding in mathematics, and he was also did not know how to go ahead with this. There were no mentors basically in India. So he was desperate, and at that time, some of his friends suggested him to write to some distinguished established mathematicians in England. He did so. He wrote to a number of mathematicians with in a letter with his results, asking help from them. But most people did not respond. And those who responded also, they did not understand much of his mathematics. Then again, with the advice of some of his well-wishers, he wrote to Hardy, G.H. Hardy, on January 16th, 1913, that he wrote a letter to Hardy. Come to that later, but this is not that one. This you can see 1918. So this is a way that Ramanujan used to write, dear Mr. Hardy, as you can see. And the signature was Ramanujan's signature will be like that, S. Ramanujan. And so this is not that letter, but the letter starts like this. So the letter begins with that, which is now very famous, that I beg to introduce myself to you as a clerk. So at that time when he was writing to Hardy, some people helped him to get a clerk's post in the Port Trust of Madras, and with a small amount of very meager salary. That way somehow he was managing his family in Madras. So I beg to introduce myself as a clerk. I have no university education. I have not trodden through the conventional regular courses. That's what I told. He gave up going through traditional way of learning. But I am striking out a new path for myself. And the results I get are termed by local mathematicians as startling. That's how he begins the letter to Hardy. The letter goes on for about 7 to 8 pages of mathematics, formulas, and he wrote something that made people think he was in fact crazy. So this is the thing, most people is a very well spoken. People keep on asking that how it can become -1 by 12 when you are adding 1 plus 2 plus 3. So that also was there in the letter with Ramanujan, what Ramanujan wrote to Hardy, and he had a way of doing it. This is not the usual convergence that you know. So people who are in analytic number theory, certainly Sandeep is there. Sandeep knows that this is so-called people who know zeta function. This is like zeta of -1, and we know the value. But of course, zeta is not directly you cannot put -1. So you have to have this what is called analytic continuation. That's called zeta regularization. You have to regularize zeta to the whole thing, then you can evaluate. But what Ramanujan was doing at that time, maybe you multiply this one by 4. This let's call it C equals to this. I mean, you cannot write because it is not convergent, but still you can write C as this. 4 times C is this. Then you write C minus 4C. So that will be like 1 minus 2 minus 3, etc. So the right hand sum is like it will turn out to be 1/3 if you evaluate at -1. So C will be like -1/12. So this is what exactly in zeta function and Dedekind eta function has a relationship, which has which has analytic continuation throughout the line, and you can evaluate that one at -1, and exactly the value comes out. So this is what is -4C minus multiplying by 4. This is exactly the way it turns out that. So it is not the usual convergence. It has to be understood that, it's a value of zeta function at -1, and the zeta function has to be analytically continued to the whole year. That is what is called the zeta regularization. So people thought that he's crazy because, people who are seeing this one first time, not first time certainly, but, it's not infinity, not even a positive number, it's a negative fraction. So if you show this one to some arbitrary person who knows just summing up things, they will think that you are talking nonsense, but he was not talking nonsense. Of course, those, as I told you, if you know Riemann zeta function, you can figure it out. Those of us do not have the knowledge in analytic number theory would find this is shocking. Like, how can 1 + 2 + 3 be a definite number, and that too a negative number and a fraction? So Hardy, by the way, was an analytic number theorist, and he immediately recognized its brilliance in connection to the work of Riemann. That's what I was calling. So he understood the depth of the mathematics that Ramanujan was doing, and Ramanujan finally found someone who understood him. So that's how this connection got established through that letter at that time. Hardy went through the other pages. As I told you, the letter was like 7 to 8 pages, and found some of them are wrong, and some of them were already known. As Ramanujan was living in a kind of a academic desert, nobody was able to tell him that whether this is a new result, whether this is a right result. That was also not there in and around of his where he was staying. So the letter ended with this one. This is, many of us know now, this is so-called continued fraction. So if you write x equal to 1 by 1 plus 1 by 1 plus, go on like that, then it is not difficult to find what is your x. So you can add or subtract 1, and then it will x will become 1 by x plus 1, and this, and then you will find x equal to -1. This number is also well known, square root of 5 over 2. It's not the thing. So what he did, related to this one, a problem what is famously known now as Rogers-Ramanujan continued fraction. So that was by Ramanujan and also by Rogers independently. So he defined what is R of Q. R of Q is actually comes out again. Sandeep does in modular forms and all. So you'll be knowing it is like a quotient of two functions G mod H, where this Q is like you can take as e power 2 pi I z. And so this is a very important thing. So when you put Q equals to 1, actually you get back the previous one, the previous slide I showed you. So this is a generalized version of that R1. And you put Q here, Q equal to 1, you get the previous one. And question is that what value of Q gives a nice answer here. Ramanujan claimed that he can evaluate e power minus pi square root of an R of these values for any positive rational n here. For example, you get that formula that he took n is as 4, and then e to the power minus 2 pi, and he related this, a golden ratio, phi is the golden ratio of with this particular number, and that he could do it for any positive rational n. That's what the claim is there. Just for an example, he gave this formula too. He did not give a proof. He just gave this formula in the letter to Hardy. Hardy thought the claim is simply out of the world, because he did not know how he got this thing, because this has a lot of other applications, not just, I'm just telling you that, there is something called algebraicity of some numbers and all. So this result of Ramanujan gives about information about those things also. And anyway, Rogers-Ramanujan's identities are being used in many, many other contexts also. He invites him to Cambridge. So this is here Hardy's take. Hardy, in fact, told, again famously, that the letter, it's just that particular letter which has, perplexed and, he was surprised. Hardy, they defeated me completely. I had never seen anything in the least like them before. A single look at them is enough to show that they could only be written down by a mathematician of the highest class. They must be true. He did not know how to do it. Whether it is correct or wrong, that also he cannot say. But he says that they must be true, because if they were not true, no one would have had the imagination to invent them. So his taking was that the right hand side, left hand side is this one, the right hand side is the answer. How do one get that one? Unless it is correct, it cannot happen. So that was the take of Hardy on the letter that Ramanujan had sent to him. So let's go back to that temple, which has also, as I told you, had played a major role in Ramanujan's journey of that short span of life of 32 years. So Ramanujan's parents never stopped supporting him, even though he had very difficult time at Madras at the time. They never discouraged him or forced him kind of thing that, you quit all these things and you take up a job at any cost to run the family. He was highly religious and he was from a very orthodox family. And when he was at Kumbakonam, he would spend most of his time in the nearby Sarangapani temple. So this is called Sarangapani, is Vishnu temple. This temple is very, very beautiful. This is another place that you have to go if you are in Kumbakonam. So I'll show his house, the outer part of his house. You will see that, there's a window there, just you enter the house. And near the window, there's a table, stool kind of things there, even now there. So he used to sit there. There will be a small table. Listen to the drum beating from this temple. And the passerby, there's a road just next to that one. So people will be coming and going. He'll be looking at that, listening to this drum beating, and will be doing his mathematics. I went to the temple. I request you to go also. And the deity, you can go upstairs there. Most places they won't allow, but here they will allow you. I hope they're still doing it. And sorry. So you go upstairs and you will see that it's full of numbers. The whole wall upstairs, if you go where the deity is, then go up and you will see the numbers there. I was looking for that famous number 1729, did not find it, but I'm sure if you give a little more time, you will find that number there. So this temple, a hard plate, and you go to the temple, again, you can feel that, if you know about Ramanujan, you know about his life, you will have a feeling that, there is some energy, some kind of special thing is there in that temple. His marriage, which is also a very important, important saga in his life. He was 21 at the time when he got married, and she was barely 10. In 1909, Ramanujan got married to Janaki Ammal, and she was 10, but the custom was there that up to 12, not before 12, that a girl can join to her husband. So she was 2 years with her parents. And then when she attained that age of 12, she joined Ramanujan, and Ramanujan with his mother and his wife, they were there in Madras. Janaki Ammal, I was giving a similar talk somewhere, I don't remember now. So somebody commented that, this famous mathematician, look at his wife, is such an unknown person. He made that comment, not to me, but I overheard him saying. So I stopped my talk and I told him that please do read a little bit about Janaki Ammal. Just imagine a lady, widowed at such an early age, acute poverty. Nobody looked after her. She had to come back from house to her own family's. I think they were also not very well off. She used to do stitching clothes at home. And whatever little bit money she earned, she used to help orphan children to pursue their study. So she continued that thing, what Ramanujan brought into us. And, someday I'm still doing some research on her life. Would like to give a talk on Janaki Ammal. It's a lady at the last stage of her life. She was helped by West Bengal government when she was almost dying, living in acute poverty. West Bengal government, somebody went there, found that one, they helped a little bit, and then the help came pouring in. But by then her life was almost over. Anyway, that's another story for some other day. So I told you that 1912, just before writing the letter to Hardy, he managed to get a job with the help of some well-wisher at Madras Port Trust with a very, very small salary. And after she attained her age of 12, Janaki joined Ramanujan with Ramanujan's mother. But Ramanujan, as always, with the job also, he continued his pursuit in research in mathematics. Another thing, without telling that the life of Ramanujan cannot be complete, is their family deity, family goddess, which is Namagiri Thayar. So in 1914, as we saw that Hardy invited Ramanujan to come to Cambridge after that letter, and he was convinced that it's a great talent and has to be mentored. And Ramanujan was from very orthodox family. He himself was very religious, but not so much orthodox. Orthodox, of course, that, as you know, that he was not eating everything. And then, but his family really used to believe that people go abroad, crossing the sea, then no more Hindus, they will be there. So it has to be disbanded from the family and should be thrown out family. So that was a complex problem at that time, which bothered him a lot. He wanted to go pursue his mathematics, but not getting permission from the family to go to England. So this Namagiri Thayar, every day he used to pray, and as is famously known that he himself has quoted that many of his results in the dream, the goddess helped him to get those results. This is the picture. So after praying to his family deity, Namagiri Thayar, maybe I'm not pronouncing well, he declared that she has blessed the overseas trip. That's what he declared to his family, and family believed him. Janaki Ammal, at that time she was 15, wanted to go with him, but there was family pressure, and Ramanujan also did not, because he was just going, he didn't know how to manage things there, so decided not to take her along with him. A decision that he regretted later. That will tell why he regretted. This is his saga, his life with Hardy. That's also a part of, which has, if you have seen that movie, you'll see that there was fierce fighting, oral arguments with Hardy at some point, in the movie. Hardy had to tell him, just get lost. So Ramanujan never bothered to write down concrete proof because he had never had a formal education. So he was not a formal mathematician as such. Whereas Hardy was a true mathematician, and he won't accept anything without a proof. Even though he knew maybe it is correct mostly, but then without a proof, he would not accept that one. So that became a major source of conflict, because Ramanujan used to think that's a waste of time, because he thinks that was very simple, but it's not simple for most people. Hardy tried to convince him that without a concrete proof, the mathematical community certainly is not going to accept his findings. He kept on convincing Ramanujan that common ground was required really to talk mathematics. And he needs a formal training for that one, to really see how to write mathematics, how to argue logically. So at some point, they both started understanding each other. Ramanujan realized the importance of formal writing, and Hardy realized that he has a genius in hand and he has to mentor him. So he wrote about 30 research papers. Some of them are jointly with Hardy, and most of them are single-authored paper. And it was the World War time, and that impacted England also. Ramanujan was working at that time at Trinity College. He was a pure vegetarian, as I told, very religious, orthodox. So he was unable to eat most of the food that was available there in England. So there was a war going on in the background, and then he had a severe difficulty at this time. He really missed Janaki. Who knows, if Janaki had gone with him, the things would have been different. He really missed at that time many of his things. He has mentioned that. Despite these hardships, for his path-breaking results, he was elected the Fellow of Royal Society, the first Indian to receive it. Of course, that had to happen due to malnutrition. He was not eating well. He fell seriously ill and returned back to India. His illness became so severe that he died 1 year after returning back in 1920 at the age of 32. In the deathbed also, he continued to produce mind-blowing mathematics on his, even though he was, not feeling well at all. He wrote only one letter to Hardy after returning back, And there he explained the mathematics that he was doing, and he wanted to return back to England, which, as you know, we all know that did not happen. So Ramanujan's mathematics has inspired the mathematics of future. This is a little bit of story that is not story. These are all facts I wanted to tell you to give you a feeling, a flavor of the life with mathematics, what is going on, and the life that he was leading. I hope I could give a little bit of an idea. So let's see what are the future mathematics that has a few I have written. As Sandeep has pointed out, there are many, many other areas which is being influenced by his mathematics. Well conjectures, which will tell a little bit about that one, not much. And by solving this conjecture, Pierre Delin got Fields Medal in 1975, which has to do with Ramanujan's work. Then there is at 1998, Borchers, Richard Borchers, he got Fields Medal, won what is called Monstrous Moonshine. That also has link with Ramanujan work. So this monster is a simple group, which is the largest group, finite group, which is very sporadic. There are some families, and this is not in that family. Its order is about 10 into, approximately 10 to the power 53. So you can imagine how big it is. And so this conjecture was by Conway and other people. It was related to some irreducible representations of this monster group. And that has something to do with the Mach theta functions that Ramanujan, I will come to that one, was talking about, and with J function. And that has its initiative from, the motivation from, encouragement from Ramanujan. And of course, the proof of Fermat's last theorem, which by Andrew Wiles. So this is the thing. I don't go much into that one. This deathbed, he wrote to Hardy that, what is called Mach theta function. He wrote to Hardy, that will come to that one, that he's doing, that he introduced what is called Mach theta functions during his that 1 year what he was there in India. And that's one of the most exciting research area in modern mathematics. And these are called Mach modular forms or Mach or mass forms. So let me go into few of the gems, whatever, 15, 20 minutes, or whatever I'm left with. So partition function, as Sandeep was telling, is some marvel gem of work is there from Ramanujan. And so partition function, all of you know, it represents the number of possible partitions breaking of a non-negative integer n. The order is immaterial. For example, if you want to write 4, you can write 4 as 3 plus 1, 2 plus 2, 2 plus 1, 1 plus 1, and 1 plus 1 4 times. So P of 4 is 5. Okay, similarly, you can go on doing it, and you can see that for 8, it is number of partitions is 22, and 16 is 232. And you can see if you go to 200, it's like 4 into 10 to the power 12. Approximately that many partitions will be there. So the number, it's a function P, apply on a non-negative integer, and it gives an output. What is the output? Output is the number of ways differentially. So there was a question that, can you give an expression for P of n for any given n positive integer? And this was a famous work, as Sandeep was mentioning. Ramanujan with Hardy, he proved that, approximately, I'll just come out, it's like e power pi square root of 2n by 3, 1 by 4 square root of 3. But this exponential thing has something to do with, the string theory. And people are now finding that, some energy with the strings. And this result, the partition functions are related, as Sandeep was also telling, has its applications in physics also, in condensed matter physics also, not just in string theory. So this result has influenced many other things in physics also. And so this tweak that I have given means that if n goes to infinity, the ratio Pn by this one will tend to 1. That's almost will be equal to that. And not just the result, the technique that they introduced in this particular famous work of Ramanujan and Hardy is called circle method. And this is still the most potent tool, most important tool in analytic number theory and in combinatorics, which people follow. In fact, now in every branch of number theory, the circle method has become a famous tool and most useful tool, and that was credit of Ramanujan with Hardy. These two congruences, which I cannot just miss, is that so beautiful, because I have also worked a little bit in partition function. He noticed, of course, this beautiful congruence that I'm going to come and will tell you how beautiful it is. Just like the partition n formula, you can imagine how difficult that is. And this one, you will see the beauty of that, these partition functions. And he did it by hand, by calculations, and then finally he conjectured, and he proved out of two of them, and the third one was proven by Atkin. But look at these three most beautiful congruences. The first one says that if you take any integer, which is like 4 mod 5, that means you subtract 4, 5 will divide that particular integer. And if you apply P on that one, whatever big this number is. So you can see, if you don't know congruence, you can see this kind of numbers. This is 5n plus 4. In this arithmetic progression, you will have this kind of numbers. It goes on, infinitely many numbers will be there. You apply P on them, 5 will always divide. So this 5 here, same as this 5 here. And just by doing few calculations, as you can see, it is not easy to do by hand, writing down as the numbers grow. And he could conjecture these things. And finally, he gave a proof of this also. The second one, as you would expect, that obviously for 5, why not for 7? And that actually happens, that if you take 7n plus 5, look at 4 has become 5. 5 has gone to the next prime. And the modulus also is 5 to 7. And actually, this happens for 7n plus 5 type of numbers also. Subtract 5, and it is divisible by 7. The partition function on that one is also, the output is also divisible by 7. So again, these are the kind of numbers, which is 5n plus 4 or 7 type of numbers. And then 7 will divide that particular output. Similarly, for 11, the next prime, 5 goes to 6 here. The 7 becomes 11 and modulus 11. This is also true, and it was proven by Atkin. Not only that, what he mentioned, that it is highly unlikely that there is no such congruence for any other primes. Look at how much depth a person, how much vision a person can have to really make that statement, that for no other primes there will be any such beautiful, simple congruences. And this statement actually was later proved to be true. Then Rogers Ramanujan's identities, I gave you one, and then there are quite a few of them, not just going into that one. And actually, not just these identities, as you can see, that there is a summation here, there is a product here. So number theories for mathematics, this is very interesting whenever you have some summation on the left, and you can write it as a product over some integers. And these are the two famous Roger Ramanujan identities. And actually, he proved, and he gave partition theoretic description also. So it's kind of partitions that represents the number of partitions of n into parts, any two of which differ by at least 2. This is a special kind of partition. And then he gives a relationship with those identities with this kind of partitions. Again, some congruences with that one. Similarly, those two famous Roger Ramanujan identities have this beautiful, a partition theoretic description, which was given by Ramanujan. Now, quadratic form, this is also another very, very important result, which has motivated lots of other people. So cannot miss this one. This is a quadratic form. Many of you know it's degree 2, it's two variables. And there is this famous result of Lagrange, 1770. It's also real marvel of number theory that, you can take any positive whole number, natural number. If all these natural numbers, take any of them, is expressible as a sum of 4 squares. For example, like this. So this is called famous 4 square theorem of Lagrange. So take any natural number. Every natural number has this form. So this is like a quadratic form, special type like diagonal quadratic form. No coefficient is there. So these are something called universal Z forms. So like a square plus b square plus c square plus d square. This is a universal Z form, means every positive integer can be expressed by this, can be written in this form. That means it's a solution. You'll find always some a, x, y, z, w, which will give you that integer. So this was Lagrange. And the question was that what kind of other forms, like can you add some coefficients here and still they will be universal Z form? So that's the question that Ramanujan was interested in. And in fact, in his classical paper in 1910, he gave 55 more such examples. Some of them are here. That was like this kind of thing. As you can see, this is the classical one, Lagrange. Then you can see he has put a 2 here. So this is not the diagonal one, and up to 7. But the 8th one actually misses a number. So this misses 7. This is some examples. This one also was mentioned in his paper. So this result of Ramanujan actually encouraged the so-called the famous 15th theorem. People who know, again the question will come that what about a generalized quadratic form like positive definite quadratic form? Do they represent all the integers? And that was by Conway and Schoenberger. This is a very famous theorem that if they represent integers up to 15, they will represent all. And in fact, they have written in the paper that this work is motivated by the exploration of Ramanujan. And of course, after that, people who know that Manjul has also beautiful results in this direction, Manjul Bhargava. So let's not go into that one. This has relationship with elliptic curves and class numbers. So this is the entrance of Ramanujan's house, the renovated one. Not much of renovation, it's just to survive, just to keep that in structure going. So this is the window I was telling, and this is the entrance. So there is a stool you will see there, a table will be there. And he will be sitting here for hours and listening to the drum beatings I was telling, and then we'll be doing his mathematics. Just here, the road will be here, still there, but that it has become a marketplace right now. So this house is kind of a singularity in that vicinity. Nearby is a very active market, but this house stands there as a memento to tell us that, there is this genius used to stay here. Tau function, as again Sandeep was telling, is one of the most profound work. The most impactful work, as the mathematics community believe, is this work of Ramanujan, and it is named after him, this function. It has influenced many branches of mathematics. So he was interested in this function, delta z, where q is again, he was always interested in the q series. And so this is like q, you take the product of 1 minus q to the power n raised to the power 24. He was interested in this 24th power because, it has some relationship with, again, the quadratic form that sum of 24 squares. Can every integer be written as a sum of 24 squares? He was very much influenced with Lagrange's work. So the motivation or the detail is really out of scope of this talk. But as I told you, that he was interested in finding out, how this number of squares, how many, keep on increasing. Is it possible to do it? So actually, this 24 has to do with 2r is 2 into 12, 24. So he was interested into that problem also, that can it be written as a sum of 24 squares, every integer. So he was studying this one. And this delta z, actually this 2 pi to the 12 is a typo, it's not there. So it has a Fourier series or the summation expansion. And if you do it, it will be like tau n to the cube power n. I'll give the values here, tau n. So this is the Fourier coefficients, or this is an arithmetical function. The conjectures are related to this function, the behavior of this function. So this tau function is a function from natural number to integers. And so this is basically, he was interested in this one. This has a, remove this, it has a Fourier series expansion, and the coefficients are what is named after Ramanujan. He was interested in this particular coefficients. And this has this beautiful relationship with the divisor function. Divisor function is simply another very popular function, which is like sigma 11n in this case. So this is like divisor, take all the divisors of n raised to the power 11 and sum them up, all divisors of n. So this is what is sigma 11n. So you can see this tau n has relationship with this sigma 11n. And so this is a beautiful result that he had with him. And it has a generalized, if you look at the generating function like tau n x to the power n, you expand that one, then you get these values of the tau tau values. Like tau of 2 is minus 24, tau of 3 is 252, tau 1 is 147. It goes on in that way. So he was, did lots and lots of calculations of these tau values, and he predicted certain remarkable properties, conjectured certain remarkable properties of this tau function, like this here, that tau of mn is tau m tau n. So this is what is called the multiplicative nature of the function, that you, for example, tau of 15. So GCD, I mean, there should be co-prime. GCD of mn should be 1. Then only it happens, not for every mn. So tau of mn, like tau of 15, 15 is 3 into 5. 3 and 5 are prime, so they are co-prime to each other. So if you know the value of tau of 3 and tau of 5, you know the value of tau of 15. So he was using that properties. Like if you know for any power of primes 1 extra, you get by knowing the previous ones. So that explains. These are very deep meanings in the setup of modular forms, in the setup of elliptic curves, in the setup of representations, automorphic forms. And still, the best part of that one is this: the tau of absolute value of tau of any prime cannot go beyond this, 2p to the power 11 by 2. This is a universal bound that he gave. And this and all three properties are considered to be, the modern, whatever you call modular forms, automorphic forms. This is kind of a basis of that. So these first two conjectures, he conjectured, did not prove. He just conjectured by using hand calculations. And these are not easy to calculate, as you see from that expansion. The first two conjectures was proved by Mordell, not long. Immediately after his conjectures, he announced those conjectures. But the third one is that Weil conjecture that I told, that the future mathematics that was influenced by Ramanujan's mathematics is by Pierre Delin, and he got Fields Medal for this one. He didn't prove only this, proved for all such forms, the coefficients will be, the Fourier coefficients will be for something called cusp forms, and will be bounded by this. This is the upper bound for such coefficients. And there is another conjecture which is called Lehmer conjecture on Ramanujan tau functions. The conjecture is never zero. I mean, he studied it so long back, more than 100 years back, and still we don't know how to prove it. But experimentally, empirically, it's known that we did not find any value which is zero, and people believe it. Okay, so this is a some animated picture of this delta function which Ramanujan was considering. Look at the beauty of this function, this so-called cusp form order of weight 12, that so many symmetries are there. So modular forms, or these forms which Ramanujan studied, do represent beautiful symmetry that our world also has. That we have so much color, so much beauty, so many different types of people are there in this world. So this is somehow synonyms, that kind of practical world that we have, beautiful world. So these are the properties that you can see that Ramanujan's notebook. If you see, you can see how many pages after pages he studied this tau function. So he knew the depth of this function, the importance of this function that is going to come for the next hundreds and hundreds of years. And he got a beautiful congruence. Again, I told that sigma 11 mod 691, this tau n is Ramanujan tau function is same as some divisor function, the 11th power of these divisors of n, sum of that. But people know a little bit of modular form. Here's a little bit of things. So this is the Fourier coefficient of cusp form of order 12. This is the Fourier coefficient of Eisenstein series, and here is the Fourier coefficient of cusp forms. They're totally orthogonal, to each other. But you see, modulo 691, this same. So recently I went to IIT Jammu. So Arvind Kumar was a student of our HRI, and he's a faculty now. He has generalized this congruence for other Eisenstein series and cusp forms, for automorphic representations, in fact. So this is very beautiful that, this is Fourier coefficient of a cusp form. This is Fourier coefficients of Eisenstein series. but they are same, even though those two are completely different objects, modulo 691. Okay, so this will be my last problem that I'll take it up. This without a taxi cab problem, taxi cab number, no lecture or no nothing of Ramanujan can be over. And I just want to break some of the myths that is there with this. So this is the taxi cab problem, taxi cab number, and Hardy wrote. I remember once going to see him when he was ill at Putney. So he was on the deathbed that particular year. Hardy went to see him, finding that he's very unwell. So he just to energize, just to make him a little bit more, energetic, he told him this thing, that I had written a taxi cab number 1729. The number was 1729. This is like this. And he remarked that the number seemed to be rather boring. He immediately told that, no, sir, it is a very interesting number. Which way? It is the smallest number expressible as the sum of two cubes in two different ways. So this is what happens. So 1729 is this is one way that you can write it as a sum of two cubes. This is another different way of writing this 1729 as two different ways, and this is the smallest number that he told. So Hardy was very impressed, just to show him, but Hardy knew that he was already working. He has worked in this kind of problems. The problem was known. He knew this because of his work in what is called the near misses to Fermat's last theorem. Now, Fermat's last theorem, people who don't know, is like x to the power n plus y to the power n equal to z to the power n. It's a Diophantine equation. N is an integer. So any n bigger than equal to 3, this equation don't have any non-trivial solutions. So if you take n equals to 1, it is x plus y equals to z. You have plenty of solutions, like 5 can be written as 3 plus 2, blah, blah. And then if you take x square plus y square equal to 1, it's very popular. It's a Pythagorean, sorry, x square plus y square equals to z square. This is Pythagorean problem that, like height square is base square plus that length square, that perpendicular square. So there are plenty of solutions like 3, 4, 5, take any multiple of 3, 4, 5, it is there. But as soon as you go from 2 to 3, you cannot express the sum of cubes of two integers as the cube of a number. Okay, so look at his acumen, his brilliance. He wanted to test that how far it is failing. Well, I cannot write it, even though Fermat's last theorem was not proven at that time, but people did believe, and for the 3 part it was known. Fermat himself did that one. So he was trying to categorize the numbers which has this property that might be missing just by 1. Okay, so he was interested in this kind of stuffs like 6 cube plus 8 cube. I know I cannot write as cube of a number, but how much does it miss? It just misses by 1. How much these two numbers cube of that sum of the cubes misses by just 1. And if you give a close look here, you will find 1729 is one of these numbers. So he found that 1729 when he was doing by hand these things. And actually he has a theorem, he has a paper on that one where he writes, categorizes the number which are thus near misses. Near misses means just missed by 1 to Fermat's last theorem. Otherwise, Fermat's last theorem, 3 would have been also there, if not the other exponents. So it was not the thing, but his memory, his sharpness, even at that time when he was about to die, did not reduce even an inch. And he could remember the work that he was doing. And that's why immediately that 1729 came to his mind. And he told that, it's not a boring number at all. Okay, so this is the Trinity College, a picture of Trinity College where Ramanujan was working. And as I told you that from his deathbed, he wrote Ramanujan just 1 letter after returning back to India. And that's what he writes. It was 1920. You remember 1920 he died. Dear Hardy, I'm extremely sorry for not writing to you a single letter up to now. and he wants to say, don't think I'm not doing mathematics. I discovered very interesting functions recently, which I call mock theta functions. We also call it mock theta functions. They enter into mathematics as beautifully as the ordinary theta functions. Theta functions are holomorphic functions. Some people will be knowing very, very much. It's used. It has beautiful properties. And so he said that this mock means somewhat again misses to be a theta function, but may not be missing by much. So he called them as mock theta functions. They enter into mathematics as beautifully as the ordinary theta functions. And his dream or his sayings are bearing fruits now. His vision is bearing fruits now. These mock theta functions were mystery till 2002. 1920, 2002. In 2002, a PhD thesis came out of Swegars, and he told that it is from Ramanujan's work. He showed that Ramanujan has discovered what is famous now as mass forms or mock theta functions. These mock modular forms, theta function is a modular form, are living up to Ramanujan's expectations. And it is one of the most active research area in mathematics, which deals with this kind of mock modular forms. It has connections with string theory, with black holes. Recently, Ken Ono has a fantastic paper on these mock modular forms and its relationship with black holes. So it is helping. In fact, Freeman Dyson has a famous saying that he's one of the most revered physicists, that if the day we will be able to understand these mock modular forms properly, we'll be able to understand black holes. Okay, so this is a picture of Ramanujan at University of Cambridge. You can see in the middle with the formal dress when he was getting his degree. So the legacy is this, as I understand, is that talent can be found anywhere, even in the most unexpected and unforgiving places, as we have seen in Ramanujan's case. The most unforgiving life that he had to lead, to fulfill its potential, it must be located, recognized, and then properly nurtured. Yeah, so that's the job of all of us. Thank you so much for your attention.
Thank you, Professor Kalyan. So we would like to ask the students for the online participants if they have any questions. Can we have time for one or two? There are some questions in the chat box.
I don't see there is any.
There was some comment on, I don't understand Ramanujan.
They were discussing about how he was discovering the three equations.
If there are no questions, I once again thank Kalyan sir for his nice talk and for the inspirational line at the end. Hope we also as teachers can find gems from unexpected and unforgiving places and nurture them. Thank you, sir.
Okay, thank you so much, Sandeep.
Thank you, sir. Right now, I request.
Yeah.
Now I request the dignitaries to take the dais so that we can proceed distributing the certificates and.
So, David, can I?
Yes, sir.
Can I go out?
Yes, sir. That's okay.
Yes. Thank you so much.
Yes, sir. Thank you, sir. Thank you so much for giving
No.
us
I mean, it's a pleasure, seeing all of you, and this is the little thing that certainly we can do if we can, do this thing. So
Yes,
carry on with your program. Thank you so much for inviting me.
Thank you, sir. Thank you.
Yeah.
So now I request the dignitaries to take the dais so that we can proceed distributing certificates. Yes, just come and sit here. Yes, please. Is it necessary? Yes, please. Sir, yes, sir, please come. So request, I request the participants to come over one by one, then I read out their names. I kindly request Dr. Kunjam Samprasad, HOD of the Department of Mathematics, to distribute the certificates. Yes. Ms. Nivedita. Next one is Joel Vasan.
Congratulations.
Mr. Joel Vasan. Dr. Sandeep E. Mr. Nagaraja. Mr. Balkish Banu. Ms. Swat Chetty.
Congratulations.
Ms. Swarna JB. Mr. Sharat.
Congratulations.
Ms. Jane. Ms. Shan. Ms. Shahana.
Jay. Congratulations.
Thank you, sir. Please sit. So at the outset, we would like to conclude it with a vote of thanks. I really, on the behalf of the organizing committee, would like to thank everyone who is part of this National Mathematics Day, as well as part of the National Workshop on Computational Linear Algebra and Graph Theory using Sage Math. There were a lot of hands actually behind the screen and off the screen and on the screen together. I would like to thank everyone who is part of this. I'd like to first of all thank the management who has given us permission to organize such a wonderful workshops, along with concluding a National Mathematics